In the winter of 1944, inside a dimly lit hangar outside Berlin, a captured American Sherman tank stood like an alien visitor. Its olive-drab hull was pitted and scarred from the battlefield, but its internal machinery was nearly intact. Around it gathered a team of German scientists from the Waffenamp testing division, engineers, metallurgists, and weapons analysts, tasked with uncovering why this unremarkable-looking machine refused to die on the battlefield. They had seen Shermans burned, shelled, and overturned, yet they kept reappearing, rolling forward in endless columns as if the Allies possessed an infinite supply of them. The men approached it not with awe, but with irritation. German armor doctrine valued precision, complexity, and craftsmanship. The Tiger I, with its interlocking armor and 88 gun, was a masterpiece of engineering, yet also a nightmare to produce and maintain. The Sherman, by contrast, was crude, or so they thought. As the scientists loosened bolts and removed panels, what they found began to unsettle them. The armor was not particularly thick, nor the gun exceptional. But the layout, simple, logical, and standardized, spoke of design meant for mass production, not prestige. Each component seemed built with the same philosophy: easy to make, easy to replace. The wiring looms were labeled in English and color-coded. Fuel lines could be disconnected by hand. Even the transmission could be swapped in hours rather than days. One scientist, running a hand along the welded seams, muttered that they looked rough. Another pointed out that roughness didn't matter when the welds never failed. These tanks weren't built for elegance, they were built for endurance. The Americans had chosen function over form and efficiency over perfection, and that decision was winning them the war. When the team reached the engine bay, they stopped. The power plant was not the complex, high-compression marvel they expected. It was a Continental R975 radial, an aircraft-derived engine, rugged and overbuilt, running on low-grade fuel. It looked almost primitive, yet its reliability record was legendary. One of the scientists whispered, almost reluctantly, "They've built an engine for farmers, not soldiers." The others nodded. That was exactly the point. They unbolted the engine mounts and lifted the power plant free, resting it on a metal cradle. One of the scientists, a veteran of the Panzer program, was the first to note what made the Sherman's heart so unusual. The Continental R975 radial wasn't a new design. It was built from aviation stock, a 9-cylinder air-cooled engine adapted from aircraft production lines. It didn't demand exotic metals or tight tolerances. It was, above all else, forgiving. Where a Panther or Tiger engine might seize from dust, cold, or fuel contamination, this radial kept running. It ran hot, noisy, and uneven, but it ran. They traced the oil circulation system, expecting complexity, but found simplicity instead. The pipes were thick, easily accessible, the filters simple to replace. They realized this was an engine that could be serviced under a tree by mechanics with a wrench and a hammer. The fuel system could tolerate lower-grade gasoline, a stark contrast to the high-octane blends German armor required. One engineer, leafing through captured American manuals, saw the logic spelled out clearly: ease of maintenance in the field saves lives. On the test bench, the Sherman's engine roared to life. It rattled the walls of the facility, the vibration course compared to the smooth hum of a Maybach. The Germans watched the dials stabilize, oil pressure holding steady. The cooling fans howled, drawing air through the ducts like a storm. It was crude, yes, but it was unstoppable. After the test, one of the metallurgists examined the pistons and bearings under magnification. They were not made from rare alloys. They were durable because they were thick, overbuilt, not refined. There was strength in that redundancy. A single cracked valve or dented cylinder wouldn't doom it. It would just lose a little power and keep going. That night, as snow fell outside the hangar, a German officer made a note in his report: "The American tank is not superior in quality, but in philosophy. They have designed for continuity, not perfection." He paused before adding the final line, one that captured their dawning realization. This machine was not built to impress engineers. It was built to win wars. Over the following days, the scientists continued stripping the Sherman layer by layer. Every discovery chipped away at the pride they once held in German engineering. The suspension system, for example, appeared almost laughably plain: vertical volute springs, nothing as intricate as the interleaved road wheels of a Tiger. But when they examined the components, they realized the genius was in the standardization. Each wheel assembly could be replaced independently. A damaged bogie could be unbolted and swapped in under an hour. No specialized cranes, no workshop floors polished like laboratories, just a team of soldiers, a jack, and a toolkit. Reports from the Eastern Front had already described the opposite nightmare for German armor: tanks sidelined by broken suspensions, abandoned in mud, engines overheating or freezing solid. A Tiger that broke down might require a train to move. but this Sherman, cheap, practical, and easy to service, could be back in the fight the next morning. The lesson was humiliating. Reliability had defeated refinement. The electrical system told the same story. Wires were thick and clearly color-coded. Fuse boxes were simple and labeled in plain English. Even the light bulbs shared standard threads with American trucks. The more the scientists measured, the more they understood how deeply America had integrated its production lines. The same factories producing tractors in Ohio were making tank engines in Michigan. The same suppliers producing wiring for Ford sedans were wiring the Shermans that rolled across Europe. In their notes, they began comparing component origins. The alternator bore a Ford logo. The bearings came from Timken. The radio-stamped Signal Corps U.S. Army was built by Motorola. Each part came from a different company, yet everything fit seamlessly. That was the power of mass production and interchangeable parts, concepts the Reich had admired but never mastered on this scale. One scientist, older than the rest, looked at the pile of standardized bolts and fittings spread on a table. He spoke softly, almost to himself. "They have turned warfare into industry." His assistant looked up, puzzled. "And what have we turned it into?" The older man answered without hesitation. "Artistry, and art cannot fight a factory." The deeper they went, the more uncomfortable the conclusions became. When they cut through the armor plates, they expected to find complex alloys or layered steel. Instead, they found rolled, homogeneous armor, nothing revolutionary but perfectly welded and remarkably consistent in thickness. The plates fit together with a precision that spoke not of craftsmanship, but of machinery repeating the same operation thousands of times a week. Each weld bead, though rough, told the same story: speed and quantity. Germany built tanks like sculptures. America stamped them out like appliances. In the test yard, the Germans brought in one of their own Panzer IVs for comparison. Both vehicles were similar in weight and dimensions, yet the contrast was unmistakable. The German tank was cramped, its interior filled with sharp corners and delicate fittings. The Sherman, though smaller in profile, offered space for movement, visibility, and comfort, qualities often dismissed by engineers but valued by crews who had to survive inside them. The scientists noted the fire suppression system, pressurized cylinders linked by hoses to the engine compartment and fuel tanks. If fire erupted, a crewman could pull a lever and flood the area with carbon dioxide. It was a small feature, but one that saved lives. The ammunition racks were lined with wet storage containers designed to douse sparks and explosions. The Germans had never bothered with such systems. They considered them unnecessary, even wasteful. Now they realized that each burned-out Sherman on the battlefield had likely saved its crew to fight again in a new one. They studied the turret traverse mechanism next. It was powered electrically, not by muscle. The gunner could swing the 75 cannon smoothly in seconds, tracking moving targets faster than any manual crank could. German tanks often relied on heavy gearing that required 2 men to turn under stress. It was another lesson. Automation wasn't luxury, it was efficiency. By the time the tests concluded, the chief scientist overseeing the project, a stern man who had once worked on the Tiger program, closed his notebook with a sigh. "This," he said, gesturing to the Sherman's stripped frame, "isn't a masterpiece, it's a tool, and tools, gentlemen, build empires." When the analysis ended, the Sherman sat in silence, its components scattered across worktables, its secrets laid bare. Yet the scientists understood that what they had uncovered went far beyond steel and oil. They had dissected an idea, a weapon built by a nation that treated war as an industrial problem, not an artistic pursuit. The Sherman was proof that victory belonged not to whoever built the finest machine, but to whoever could build the most that worked every time. In his final report, the lead scientist wrote, "This tank is not extraordinary in any single part, but in how every part serves a purpose." He admitted what few dared to say aloud, that German perfectionism had become its own enemy. The Americans had built a machine that could be repaired by a farmer, fueled by anyone, and replaced overnight. It didn't need to be beautiful. It only needed to move, shoot, and keep moving. Months later, as the Red Army approached from the east and Allied columns advanced from the west, one of those same scientists saw a column of Shermans grinding forward through the smoke. He murmured, "It never stopped running."